Hello everybody. We're going to take a look at the last section in Chapter 5. Before our stay-at-home orders, we had gotten almost through the end of Chapter 5. And there was one more section we needed to cover, and we skipped that, and now I'm coming back to it, and we're going to test you on Chapter 5. Just so you know, I'm going to take at least one video, or I'm going to entirely do a whole series of review. So stay tuned for that one. Don't miss that one. We're going to review completely. Your test on Chapter 5 is coming up. It will be on May the 6th. That's a Wednesday, May the 6th, on Chapter 5, the second half of Chapter 5, all about radicals. So we're going to review that section. Don't miss that review. I'm going to go entirely through a review assignment with you. All right. If you open your book up to page 270, this is a section titled Complex Numbers, page 270. This is an entirely foreign concept to anything you've done in the past. Somebody in maybe one of your other classes, other math classes, may have introduced you to this, but we're going to take a look at it, what it is. What we're going to be discussing is, in some ways, it's theoretical, but in other ways, mathematicians sometimes don't understand something, and so they have to think outside the box sometimes to help them understand something. Sometimes you'll get a problem in math, for example, 2x squared plus 2 equals 0, and mathematicians look at that and say, well, x has got to have an answer for that. But if you take a look at this, and if we solve this equation for x, we'd subtract 2 from both sides, and we divide both sides by 2, and we end up with x squared is equal to negative 1. Now we could stop here and talk about this for a minute. From what we understand about squaring something, that anything we square, whether it's positive or negative, will always end up with a positive answer. So it appears that at first glance this problem has no answer. And in the olden days, when we talked about just the real numbers, there was no answer to it. But now we're going to take a look at a new numbering system that was come up with by mathematicians to help us explain how to solve this. And somebody say, well, what's the point if these are just imaginary kind of theoretical things? Well, in reality, there are applications for this in the real world, particularly with electronics and fractals and other things in physics, that it actually does have answers that are really in the real world. So we're going to take a look at how to solve problems where we have to take the square root of both sides of something, where we take the square root, and this is now x, and now we're asking for the square root of a negative 1. In this case, it'd be plus or minus the square root of a negative 1. Well, if you put this number in your calculator and punch in the square root of negative 1, you probably get an answer that says it probably says an unreal answer on it, okay? But if you set your calculator to a certain setting, you will actually get an answer that goes in there. Let me take a look at what your calculator would do here. All right, let's take a look at this again. It says the square root of a negative 1. By the way, make sure when you're plugging in negatives you don't hit the subtraction sign. Let's see what happens if I plug in the square root of negative 1. And you notice it gives me an answer that says the error is a non-real answer. Non-real, what does that mean? Well, it's obvious that we can't take the square root of this and end up with a number that we've been used to using all along. But there is an answer for this if we set our calculator in what's called the complex number system. Let me show you where that is. Let's go back here. I'm going to go to mode, and right down here where it says real, right here, some of you it'll look a little different, but it says real here. I'm going to change this to what's called A plus BI. And A plus BI is what's called the complex number system. The fact of the matter is A is a real number and BI happens to be what we call an imaginary number. Let's see what happens if I take the square root. Now my calculator is set for this mode. Okay, so let's go back and try the same problem. Square root of -1. What do we get? Well, it gets this number called I. That is an I there. It's a little hard to see from your perspective. Now, for us to understand what we're doing, this first video I'm going to give you is all theoretical, but don't skip this video. We're going to get into some problems in the next video. But this theory is extremely important, so don't skip over this. All right, let's take a look at what this all means, okay? All right, let's go on a little journey through history of your mathematical history from the time you were little. We're going to make a Venn diagram here which talks about the sets of numbers. Sets of numbers. And you'll get that. We've done this earlier in the year, but we're going to do it here and apply it to imaginary numbers here. All right, when you were real little, the very first thing you learned probably was how to count by the counting numbers. We call those the natural numbers. 1, 2, 3, you know. N is those numbers 1, 2, and 3, and so forth, okay? And then shortly after that, somebody probably expressed to you this number 0. Well, 0 happens to be the only addition that is made in the set of whole numbers. The set of whole numbers is 0, 1, 2, 3, okay? And then sometime after that, people probably introduced you to a set of numbers where there was negatives, like maybe you had something, some money, and you owed somebody a certain amount of money. Those things called negative numbers. And so negative numbers, we use the letter Z. Z is a German word that's used to describe integers. Integers are those numbers that are positive and negative whole numbers, and 0 that go off to infinity. Okay, those are the integers. Now, this is all old news for you, and then outside of that, you learned about numbers that were called rational numbers. All of the numbers that can be made up to be fractions, for example. Okay, and fractions, we're going to put a dotted line right here. Fractions are called the rational numbers, and we use Q because Q stands for quotient. I'll put it up here now. Q is all those rational numbers. Any number that can be written as A over B, where B is not equal to 0. And A and B are integers. So all of the rational numbers. Okay? Then if there's a bunch of numbers that can be written as fractions, there's also a bunch of numbers that can't be written as fractions. And we call those I, or irrational numbers. Capital I. Capital I, don't mistake capital I with little letter I. They're not the same. Q, the rational numbers, are things like, you know, any number that can be written as a fraction, like -4 or -4/3 or 2.7. Or, you know, 6.3 repeating. Anything that can be written as a fraction are the rational numbers. And there's a lot of things that aren't rational. For example, the square root of 2. If you find the square root of 2 on your calculator, it will not give you a number that terminates, stops, or keeps repeating. Or something like pi. Pi is an irrational number. Or like we just got done covering in the section on exponentials, E is an irrational number. It doesn't stop. It keeps going forever. You know, anything like that doesn't have a pattern, like 0.1, 4, 2, 3, 7, and it keeps going on forever. Something like that. Those are all the irrational numbers. Now, up until now, that's all the numbers you've had to work with from here to here. And these we have called the real numbers. Any number that is in this group here is called the real numbers. But all of these years, there's actually been another set of numbers sticking on out here that we've never talked about. And this is the group which we call the imaginary numbers. And that's those numbers, imaginary, that's those numbers that we just introduced. The square root of any negative number. Square root of a -1, the square root of -2, square root of any number, square root of a -0.43. Anytime the square root is negative underneath, that is an imaginary number. So what you saw on the calculator, I'm going to erase this at the bottom here. What you saw on the calculator is that set of numbers, A, right here, A plus BI. BI is imaginary, and A is the real numbers. Now, up until now, in all of your math work, you never really saw BI. You had maybe had something like 2.7 plus 0i. Well, 0i is just 0, so you never really saw that. They just didn't bother to write it. But it's been there all along. Okay? And so the real part is here, and the imaginary part is here. So as you write these numbers, the real plus the imaginary is what we call the complex number system. This whole thing now, let's erase this up here. This whole thing now is called the complex number system. And you've been working in the complex number system your whole life, you just didn't know it. The complex number system, from your perspective up until now, was just the real parts. We've never looked at the imaginary parts. Not imagination, imaginary, okay? And so now when we talk about the complex number system, it's this combination of the real part plus the imaginary part, okay? These are numbers that have to be stated separately because part of that number is a real number, part of that number is an imaginary number. So, for example, let's take a look at what one typical problem might be. Okay. All right, here's a typical addition problem using actually complex numbers. This is a complex number. This is the real part. This is the imaginary part. This is the real part. This is the imaginary part. And as you can imagine, we can add the real parts together. That would be 11. And we can also add the imaginary parts just as though this I were a variable. It's not a variable, but it's just an indicator that we're dealing with the square root of a -1. So I can actually add those two together too. 2i and 3i is 5i. So the real parts can be combined any way we want to, and the imaginary parts can be combined too. So, I mean, in all these years, if you had something like 6 plus 5, you knew that the answer was 11. Because what you really didn't see was this is 6 plus 0i and 5 plus 0i. So that's 11. That's 11 plus 0i. Well, 0i is just 0, so you did get 11. You just never saw those imaginary parts all these years. And we can do this with we can add, subtract, multiply, and divide, and do other functions as well on imaginary numbers. And in many ways, it's just like working with a variable. Let's look at another one with multiplication. There you go. Now, by the way, you'll notice that I'm curling my eyes. Make sure you do that so people can tell it's not just a 1 or something there. Here I'm multiplying two complex numbers together. Again, complex is this combination of real and imaginary. Real and imaginary, okay? But now we can multiply just like we would any normal binomials. We're going to FOIL this the same way. So here we go. 4 times 5 is 20. Outer 4 times 3i is 12i. 5 times 2i is 10i. And 3i times 2i gives us 6i squared. I can combine these middle terms here. This is 22i. And then there's this thing at the end called I squared. And we're going to need to talk about I squared. It's a big deal in these problems to understand. But you'll notice that we're dealing with these things just like as though they were variables, but recognizing that I has special meaning here. It's not just any old variable. It's not a variable at all. It's an indicator that the square root of a -1 is involved. So let's take a look at what this means to have I squared. All right, we're going to start here, and this the reason why this is true is just by definition. By definition, mathematicians have chosen, let's just call the square root of a -1. Let's just call it I. Okay? We're going to call it I. What would happen if I squared both sides here? Square this and square this. I'm going to square both sides. If I square both sides, let's do it right here. I find that I squared is over here as it should be. And what happens when a square and a square root? They undo each other. So a -1 is equal to I squared. Well, if we go back to the original problem we just had, I don't remember the whole problem, but part of it was 6I squared. This I squared actually is a -1. So this is 6 times a -1. I squared, from our perspective, is always going to be -1. This is a very important concept. I'm putting a box around it because it comes up all the time. Anytime you see I squared, you're going to put a -1 in there. So 6 times I squared would be 6 times a -1, or a -6. This is a key concept. Now, what happens if we go a little farther? Let's take this and go a step farther. I'm going to erase this here. By the way, please come back and look at these things over and over again if you need to. What happens now if I multiply both sides here by I again? I'm going to multiply both sides by I. Well, now I get I cubed here, and over here this is -I. Okay. Now what happens if I multiply both sides by a negative, or by I again? I'm going to multiply both sides by I. So -I times I. I've just multiplied both sides by I. On the right I get I to the 4th. And over here I get -I squared. Well, what is a -I? What is I squared? I squared is a -1. So we put in for I squared, we're going to put -1, or I to the 4th is equal to a +1. That's interesting. We started out with I being the square root of -1, right here. Then I squared is a -1. Then I to the 3rd is -I. And I to the 4th is just 1. Now, these 4 that I've got here, I'm going to pull these out and talk about them again. All 4 of these. We'll talk about them again and look at a pattern that will develop in these problems. You're going to have some homework to deal with this. So let's take a look at this pattern here. All right, I've rewritten those here. I've turned them around so the squareds and so forth are on the left here now. But I'd like you to see what happens here. I is equal to square root of -1, I squared, and this is kind of a key one for us here. I to the 3rd is a -I, and I to the 4th is just 1. Now what happens if we go a little farther? And let's multiply both sides by I again. I would get I to the 5th equals 1 times I, or I. What if I multiplied both sides by I again? I'll get I to the 6th equals I squared, which is equal to a -1 by our definition here. See, it's the same as this one. But if we multiply both sides by I again, I would get -1 times I, or -I. And what if I multiply both sides by I again? I to the 8th equals -I times I, or a -I, -I, squared. Well, what's negative I squared? Well, it's a negative 1, or 1. Now, what you'll notice here is that this and this are the same, these two are the same, these two are the same, and these two are the same. There is a pattern that has developed here. Every 4, not 2, but every 4 I factors has the pattern repeated. So I can predict what would happen if I continue on. I could predict that I to the 9th, well, let's divide that by 4. Actually, let's look for the highest multiple of 4 that goes into that. That's equal to I to the 8th times I. Well, I to the 8th is just 1, so that's equal to I. What's the highest one here? Well, let's break that up to I to the 8th times I squared. Well, I to the 8th is going to go out and just be 1 times I squared is a negative 1. Let's break this up into I to the 8th times I to the 3rd. Well, I to the 8th goes out, and I to the 3rd is a negative I. And then I to the 8th, actually, 4 is a factor of 12, so I to the 12th has to be the same as I to the 4th times I to the 4th times I to the 4th, or 1 times 1 times 1, which is 1. Notice the pattern is established here. So we can find even higher powers of this. Let me do a couple for you, showing you the higher powers here. Let's take a look. I'm going to leave this here. Let's take a look what happened. What would it be if somebody asked you for I to the 43rd? Okay. Well, what I'm looking for here now is the highest. I want to divide this by 4. And if I divide that by 4, I end up with I to the 40th. I'm sorry, I'm not dividing it by 4. What I'm doing is looking for the multiple of 4 that's just less than 43. So isn't this I to the 40th times I to the 3rd? I'm looking for a multiple right here of 4. Well, this becomes 1 and goes out, and this is just I to the 3rd, or a negative I. Look up here, okay? Let's do another one. I to the 99th. Well, let's do a different one. How about I to the 97th? Okay. Well, what's the highest multiple of 4 that is just less than this? Well, that would be I to the 96 times I to the 1st. 96 and 1 is 97. 96 is a multiple of 4, so that goes out, becomes 1, and this is simply I. Let's do another one. I to the, how about 36th? What's a multiple of 4 that is equal to or just less than this? Well, it happens to be 36. So I to the 36 is just equal to 1. Let's do another one. How about I to the, 18th? Okay. Well, what's a multiple of 4 equal to or just less than 18? That would be I to the 16 times I squared. Well, that's a multiple of 4. It's the 4th multiple, so that just turns into 1. And I end up with I squared, which happens to be negative 1. Now, if you need to come back and look at this, you can. It's also talked about in your book. This is not terribly important. The most important thing we need to remember is that I squared is equal to a negative 1. I know this is a strange idea, and it does have applications in the real world. Let's look at solving some other problems like simplifying radicals. That's what this chapter is all about anyway, isn't it? All right, let's take a look at this one. Notice it's got a negative under the radical. So this answer can't be a real answer. It's got to be a complex answer. Or it could be a solitary imaginary number. We'll see, okay? Well, what we're going to do is we're going to break this up into all of its perfect square factors, just like we've always done. See, there's a square root out here. So we're going to break this up into all the perfect square factors. By the way, at the top here, I put the two most important things you need to remember in this section. Okay? Let's break this up into all the perfect square factors. Well, we know that 18 can be written as 9 times 2, but I got a negative in here as well. So that's negative 1. Now, I've broken this up into all of its perfect square factors and then the ones that aren't perfect squares. If you recall, I've always circled the ones that are going to come out. The square root of 9 is a perfect square. And now the square root of negative 1 is also a perfect square. The perfect square, the square root of negative 1 is I. So if I take the square root of 9, I'll get 3. I get the square root of negative 1, which is I. Square root of 2 is left behind. The 2 does not come out. I've taken out all the perfect square factors. This is simplifying the radicals the way you've done before. Let's look at another one here. Square root of negative 125, x to the 5th. Okay. We're going to break this apart. Maybe this is a long time since you've done this, so you'll probably have to review a little bit. We're going to break this up into all of its perfect square factors, and then there's going to be some that aren't perfect squares. Okay. Well, I'm going to start by the fact that there's a negative out here. Negative 1 is a perfect square factor. See that right there? Right there. Okay. 125 is not a perfect square, but 25 times 5 is a factorization of that. There's a perfect square. So this is a perfect square, and this is a perfect square. And x to the 5th, well, we can break that up into x to the 4th times x. Now, why did I pick x to the 4th? Because remember, we take the square root of things, we're going to divide those powers by 2. This is also a perfect square factor. Remember that? It's an even exponent, so I can divide it by 2. So we're going to take the square root of these three things that are circled. The square root of negative 1 is I. Square root of 25 is 5. And the square root of x to the 4th is x squared. And what doesn't come out is the 5 and the x. You'll notice I wrote the I last here. That's kind of normal procedure. You're going to look for the perfect square factors. And remember now, this is really not much different than what we did before. But now negative 1 is a perfect square factor. Let's try a couple more of these. All right. Now, here is one thing that is a little different than we've done in the past. In the past, if you had two square roots, you just multiplied them together. For example, the square root of 2 times the square root of 3, you could just multiply them together and call it the square root of 6. Okay? If we do that here, what's going to end up happening is we're going to end up with a square root of a positive number. And the idea of a negative square root is going to get lost. So we can't just multiply these together. Don't multiply them together. We're going to actually write them this way. We're going to write it this way. The square root of a negative 1 times 10 times the square root of a negative 1 times 15. Now, which of these are perfect squares? Well, that's a perfect square. And that's a perfect square. So we're going to take those out. This is I root 10. And this is I root 15. And if we combine these, we see we have I squared times the square root of 1. Now, I can simplify that, I think, a little bit, can't I? Yeah, this is actually, let's see, 5 times 150 would be 25 times 6, is that right? Yeah, 25 times 6. That's 150, isn't it? Yeah, it is. And this is a perfect square. This is 150. Let me write that out so we don't skip too much here. This is the square root of 150, which is I squared times the square root of 25 times 6. Well, of course, 25 is a perfect square. So now I've got 5 I squared root 6. But now, before we walk away from this, let's remember that I squared can be simplified. Look at that. I squared is actually, whoops, this should say a negative 1 here, not positive 1. I squared is a negative 1. Some of you may have noticed that at the top of the problem and didn't say anything. Okay? So if I squared is a negative 1, we end up with 5 times a negative 1 times the square root of 6, or negative 5 square root of 6. Let's do another one of these where both the numbers are negative. Okay? All right, let's take a look at this one. Now, because there's negative radicals here, I'm going to have I involved somehow. Okay? I don't want to just multiply these two together and get the square root of 160, because now the negative have been destroyed and I can't see that I is really involved. So I'm going to call this the square root of negative 1 times 4 times 2. Again, these are perfect squares. And I'm going to call this the square root of negative 1 times 4 times 5. Again, these are the perfect squares. They're coming out. So let's take the square root of a negative 1, that's I, and the square root of 4 is 2. I'll put it up in the front here. See that? Square root of 4 is 2. Square root of negative 1 is I. Square root of 2 is still underneath there. This again is 2I root 5. Now if I combine these, I end up with 4I squared times root 10. 4I squared. The point being here is you cannot multiply two negative radicals together, negative underneath the radical, and get rid of those negatives. You'd end up destroying the I value here. Now, I squared is a negative 1. I squared is a negative 1. So this is 4 times a negative 1 times the square root of 10, or negative 4 root 10. You're going to have some of these to practice tonight. Your book explains it pretty well. If you need to come back and look at the problems again here that I've done, do that. All right, let's do a few problems, and I'm going to do several today. The video is going to be a little longer, but let's do several problems today from your homework. This is on page 273. Okay, number 4, the square root of negative 36. Well, 36 is a perfect square, and negative 1 is a perfect square, right? Remember that? Negative 1 is a perfect square. It gives us I. So this is 6I. Square root of 36 comes out, becomes 6. Square root of negative 1 comes out, becomes I. I suggest you write these two at the top of your paper so they're constantly a reminder to you what you're doing. Okay? Let's take a look at number 5. Okay? The square root of negative 50, x squared, y squared. Okay? All right. Well, I noticed that x squared is a perfect square, and so is y squared. So this is a negative 1 times the perfect square factor of this would be 25. And I'm going to take everything out except for the 2. The square root of x squared is x, the square root of y squared is y. So here we go. 5. Square root of x squared is x. Square root of y squared is y. Square root of a negative 1 is I. And then what's left over that didn't come out was the 2. There you go. Now, this is not a big deal here, but I just want to remind you that there's going to have to be absolute value on this problem. If you remember, anytime something starts out with an even exponent under the radical, under the square root radical, and it ends up odd, these are odd here, they're both 1s, right? If it ends up that it turns out that a variable starts out even and ends up odd, we really need to put those pieces in absolute value. So I'll just combine them and put them in the same. Now this is not a big deal. You may end up seeing that on a question. Just remember that if it starts even and ends up odd, you're going to end up having to put absolute value on it. Boy, that's a long time ago, isn't it? Let's do another one. All right, let's take a look at number 6 here. If I multiply these two together, I get negative 12I squared. You notice we're dealing with I just like you would normally deal with a variable. Okay, in many ways that's true. The way we operate with it just looks like a variable. Now, I squared happens to be negative 1, so what I really got is negative 12 times a negative 1, or a positive 12. Number 7, 5 root negative 24 times 3 root negative 18. Now, once again, we can't just multiply these two negatives together. We're going to break them apart into their perfect square factors. So here we go. Negative 1 is a perfect square. There's a 4 in here, that's perfect. Over here, a negative 1 is a perfect square, and there's a 9 in here that's perfect. Okay. Well, this is going to take us a little extra work to do all of this here, so all right. Let's take the square root of 4, which is 2, square root of negative 1, which is I, and there's that 5 that was already there. So this is actually 10I root 6. Square root of negative 1, again, is I. And over here, the square root of negative 1 is I. The square root of 9 is 3. Times the 3 that was already there. Square root of 2. 3 times 3, this is 9I root 2. And 10I root 6. All right, now we're going to run out of room here, so I'll have to move up here in a second. All right, 10I times 9I, oops, excuse me, 10I times 9I is 90I squared times the square root of 12. 90I squared times the square root of 12. Okay, let's move up just a little bit here. Actually, I'll probably just put it up at the top up here. I have 90I squared times the square root of 12. Well, there's two things I still need to do. Can you see that, what they are? Yeah, I squared is a negative 1. And in here, the square root of 12 actually has a 4 in it now. See that? There's a 4 in there. So we're going to take the square root of 4. I've got negative 90 times 2 root 3, or my final answer would be a negative 180 root 3. You might take a look at this one again. You can have to go back and take a look again. We got to get rid of all the perfect square factors under the radical, so I couldn't leave 12 under there. I had to pull out a 4. Let's try another one of those. That's a long one. All right, that was the last one in that group, so I'm going to move on to number 8 here. It asks for I to the 29th. Okay, now, if you remember that every fourth power turns into 1. So I'm looking for a multiple just less than or equal to this of 4. Well, it turns out that would be I to the 28th. That's a multiple of 4 times I to the first. 28 plus 1 is 29. Well, I to the 28th is just 1 times I, or this is just I. Number 9. Here we got a problem that involves complex numbers, there's an I there, and subtraction. Now, as we did, this is one of the first problems I did for you. Here the real parts are, and here are the imaginary parts with the I in them. I've got to distribute this negative in first, so I'm going to do that. Get rid of these parentheses. Don't forget you got to distribute it into both parts there. Okay. Now add together the things that are real and add together the things that are imaginary. So 8 minus 2 is 6. 6i minus 3i is just 3i. So there's your answer there. You don't need to overthink this one a little bit. It's just like dealing with variables. Number 10. All right, here's number 10. You can see that we're going to FOIL this. Okay, so here we go. 3 times 4 is 12. 3 times 6i, outer terms, is 18i. Inner terms, 4 times negative 5 is a negative 20i. And negative 5i times positive 6i is a negative 30i squared. By the way, this is the #1 mistake that's made on the test. People forget to put squared here. They just put I here for some reason, but it's I squared. Now, let's combine like terms. And while we're at it, notice that I squared is really a -1. See that? That's why you have to put these at the top as a reminder to yourself. So I've got 12. Combine these two. They're like terms, so this is -2i. And this is a -30 times a -1, or a +30. And when I add that to 12, I get 42. And I'm going to write my answer with the real part first, then the imaginary part. Again, make sure you're curling your eyes there. Let's do one more, and this kind of is the most complicated thing you're going to see on your assignment tonight. All right. You know, the instructions on all these problems I've been doing for you just simply said simplify. And if you recall, simplify means we can't leave a radical in the denominator. Well, what is I? Well, I is a radical. I is a radical, so we can't leave I in the denominator. Also, I can't just cancel these because they're add-ins, so you don't just cancel. Do you remember how we got rid of a radical in the denominator? Well, in this case, because we got a binomial here, we had to multiply by the conjugate. Remember that? The conjugate. What's the conjugate of this? Oh yeah, I'm going to multiply top and bottom by 1 minus 4i. And if you recall, the reason we did that is it caused the middle terms to go out. And we're hoping that that will work and get rid of this I in the denominator. In fact, it will. So we're going to FOIL both of these. The top is a binomial times a binomial, so we have to FOIL that as well. So here we go. 3 times 1. I'll put parentheses here so maybe it looks a little bit better. 3 times 1 is 3. Outer would be a -12i. Inner is plus 1i. And last is a -4i squared. On the bottom, 1 times 1 is 1. Outer term is -4i. Inner term is a +4i. Oh, good. Those are going to go out. And then last terms would be -16i squared. So what we were counting on is going to happen. This is going out as expected. And this I squared is actually going to change because we know that I squared is a -1. So that's going to change to a -1 right here. Okay, so let's rewrite it. I'm going to combine terms now. Oh, this is also going to change to a -1, isn't it? So what I've got is 3 minus 11i plus 4 on the top. -1 times a -4 is a +4. And on the bottom, I get 1 plus 16. How did I get 16? -16 times a -1. I squared is a -1. So -1 times -4 is 4. -1 times -16 is 16. So our final answer here is 7 minus 11i all over 17. That's the correct answer. However, your book kind of prefers that we write it a certain way, and that is separate the real part. See, this is the real part here from the imaginary part here. So the real part is 7 over 17, and the imaginary part is a -11i over 17. This is really the way your book's going to present the answer, and I think you'll see that on most tests as well. Separate the real part from the imaginary part when you write your answers. Okay, these are both correct answers, but this is the form that's really requested. All right, let's take a look at your homework for tonight. All right, here's your homework for tonight. And we've already done a bunch of these, like 4 through 11. I want you to practice some more of these tonight. Get really good with this. If you need to watch the video again, this was a long video, and there's no way we can get around understanding this concept without understanding sort of the foundation of it all. Go back and watch it again. I know it may take you a little extra time there, but you need to do that. Assignment's not real long after that. Make sure you write these two things at the top of your homework. Square root of -1 is I, and I squared is a -1. The test on this chapter, this is chapter 5b, is on radicals. Okay, that's going to be Wednesday, May the 6th at 6:55 p.m. Tomorrow we'll show you another video on how to solve equations here. All right, enjoy yourself. Have a good time. Enjoying complex numbers. You're complex thinkers now.